There are three major kinematics equations. We've covered number one in depth. Now it's time to move on to number two. This slide truly shows the beauty of physics and mathematics. We have three equations. We have a definition for the average velocity, which is displacement over time. We have another definition for the average velocity that holds true for constant acceleration, where it's v final plus initial velocity divided by 2. And we have the first kinematics equation, which actually came from the definition of acceleration. So let's walk through this. We start with this equation here, and we multiply through by time. So you get displacement is average velocity times time. Then take this equation and follow the arrow. We substitute that in for average velocity. So we now have this equation. And we also use the definition of displacement, which is x minus x0, final position minus initial, equals 1/2 v plus v0 times t. Then we use the distributive property of math. We multiply through this 1/2. So you can now see we have 1/2 vt plus 1/2 v0t. Do a little rearranging here. Take this x0, put it on the other side. So at this point we have x is equal to x0 plus 1/2 v0t plus 1/2 vt. Let's look at this term right here. We have the final velocity. Well, we know how to find the final velocity given the initial velocity and the acceleration from Kinematics Equation 1. So we take this, move that in, and we put that in for v, and we now have this equation. So you can see any one step is pretty straightforward. It just looks fairly complicated if you look at the whole page as one. So here we have kinematics equation number 1. We use the distributive property of math again, multiply through by 1/2. Then you get 1/2 v0t plus 1/2 at squared. And let's see, can we combine anything? Yes, we can. Look at this right here. When I add those two together, we get final position equals your initial position plus your initial velocity times time plus 1/2 at squared. That now directly tells us the position of an object as a function of time, as long as we know its initial velocity and its acceleration. This is a very powerful equation, and this is kinematics equation number 2. Let's now derive kinematics equation number 2 using a different type of math. We're going to use a graphical approach. This happens quite a bit in math and physics. There's many ways to come up with the answer. Let's take a case where we have a constant velocity, and we are going to use a velocity time graph, and notice how both axes are properly labeled with the variable and the time, and we're going to draw a constant velocity here, v0. We have a rectangle here. We know that the area of a rectangle is length times width, so the area of this rectangle is going to be your initial velocity, that's your height here, or your width, and your length is going to be time. So the area equals v0t. Now we also happen to know that velocity is equal to the displacement over time. So in this case, the area is really, if we have, let's just multiply this through, we have velocity time equals displacement. So this curve here, the area is displacement is v0t. So we have delta x is equal to v0t. That's what we find from this graph. Using a velocity time graph again, we're going to have a velocity that increases uniformly in a straight line, which means that the acceleration is constant. So if we take this point here, we have a final velocity like so, and then we have an elapsed time here. And if we just look at the area under this curve here, under the velocity line, we know that the area of a triangle is 1/2 times base times height. So the base here is time, and then the height is velocity. So we have the area under the curve is 1/2 delta v times t. Now, a, acceleration, is delta v over t. So we have delta v equals at. We just multiplied through by t, and we substitute this in right over here for that delta v. So we have the area is delta x, which equals 1/2 t times at, which is 1/2 at squared. So this is the contribution to the displacement due to the acceleration of this object that's moving. We've now shown in the previous two slides that the area under this curve, whether it's horizontal or diagonal here, it's basically velocity times time, which is displacement. So now let's consider the case of an object that starts here with a certain initial velocity and then accelerates. Its velocity keeps increasing. And we want to find the total area under this curve, which will give us its displacement. Well, it certainly has a contribution from just your initial velocity times time. Then it also has a contribution from the acceleration. So if we add these two characters that we came with on the previous two slides, we get the area under the curve is the displacement of the object, and it's equal to v0t, that's from the rectangle, plus 1/2 at squared, that's from the triangle. So we break delta x into x minus x0, and that's still equal to v0t plus 1/2 at squared. We add x0 to both sides, and right over here, again, we have the second kinematics equation, this time derived through a graphical approach.